Okay, guys, so we are jumping into section 7.3. We're still talking about probability and statistics. And so here we're going to be looking at something called binomial trials, and more particularly the binomial probability distribution. So this is a famous and very useful probability distribution that we can use to calculate probabilities in a number of different contexts. Okay, so let's go over some basic definitions first and notation. So we're going to define what a binomial trial is. Okay, or I should say, rather than trial, I'm going to correct this and to say this is not trial but experiment. It's a better word. So let me just correct that. So a binomial experiment is an experiment where the number of outcomes per trial, okay, so per every iteration of the experiment, the number of outcomes per trial is exactly 2. So there are only 2 outcomes for every trial, and each trial is independent. The experiment consists of not in many trials. So some fixed number of trials, and we're using the lowercase n here to represent how many trials there will be in this binomial experiment. So let me just reiterate: a binomial experiment is an experiment where there is a fixed number of trials, n, and each trial has exactly 2 outcomes, and each trial is independent from all other trials. So the probability of one outcome in a particular trial is not affected by the outcome of another trial. They're all independent. Now, since there are only 2 outcomes, we generally use the terminology of success and failure to represent one of the outcomes versus the other outcome. So there are 2 outcomes in a binomial experiment, and one of those outcomes we'll consider success, and one of those outcomes we'll consider a failure. The working example that you like to keep in your head for this discussion is flipping a coin. Flipping a coin is a perfect binomial experiment where there are 2 outcomes, heads or tails, and each trial is independent. So if I flip a coin twice, the second result is not affected by the first result. Okay. So if I consider flipping a coin my binomial experiment, then I could consider getting a heads as a success and getting a tails as a failure. This is a completely arbitrary choice, but this is a way I could choose it. And in this context, we use the lowercase p to represent the probability of getting a success, or in our thought experiment, of getting a heads, right? So the likelihood of getting a heads is P, and then the likelihood of getting a tails is Q, which is the complement of P. So that's 1 minus P. And when we call that the probability of failure. So for our working example, that would be the probability of getting a tails. Okay, so this is what we call a binomial experiment. It turns out that a lot of different phenomena can be modeled using binomial experiments, because often we're interested in whether or not something is true. Does the person have cancer or don't they have cancer? Is it a heads or is it a tails? Some sort of question that only has 2 answers. So people much smarter than either of us came up with a function that will tell you exactly what the probability of getting a certain result is in a binomial experiment. Okay, and we call this the binomial probability formula. So this starts off by defining a random variable, big X, which counts the number of successes in many independent binomial trials. So there are n many trials in the binomial experiment, and this X, this random variable, counts the number of successes out of n many attempts. Okay, so this function here actually determines the probability of getting k many successes out of n many trials, where k is some number that's less than or equal to n. Okay, so the probability of getting k many successes can be computed by taking the binomial coefficient n choose k and multiplying it by p to the kth power times q to the n minus kth power. Okay, so we've got our p and our q, our probability of success and our probability of failure. P is raised to the power that counts the number of successes that we're interested in, and q counts the number of is raised to the power n minus k, which is the number of failures. N choose k is a binomial coefficient, which we learn is computed using factorials, where it's n factorial over k factorial times n minus k factorial. Okay, so again, k and n minus k. K is the number of successes, n minus k is the number of failures. K plus n minus k adds up to n. So these are just some patterns that we see here. Okay, so this function, this formula, tells us how to compute the probability of getting a specific result. Okay, and we can use this to determine the probability distribution for different binomial experiments. Okay, so let's look at an example. Here we are looking at the random variable x that will count the number of heads out of 4 coin flips. We want to determine the probability distribution. Okay, so x counts the number of heads out of 4 coin flips. So to determine the distribution, that means we're making this table here. And the first thing we're going to do is determine the possibilities. So either we could have 0 heads, 1 heads, 2 heads, 3 heads, or 4 heads. That's the easy part. Now we need to calculate the probabilities. The good thing is we've got a formula now. So as long as we can identify all the parameters correctly, then we can use the formula. So first, what's the probability of success? Well, we're interested in flipping a heads. So the probability of success is actually 1/2, because the coin is fair, and that means the probability of getting a heads is 50%. Likewise, the probability of getting a tails is 50%, which is 1 minus 1/2. The number of trials is 4. The number of coin flips. Okay, so let's see what happens when we put this all together. If we want to use the formula to calculate the probability of getting a 0, then that's going to be 4 choose 0 times 1/2 to the 0 power times 1/2 to the 4th power. This is following exactly the formula that we have using these parameters. So let's figure out what all this is. To figure out the binomial coefficient, I showed you this in the problem session. To figure out 4 choose 0, we put the number 4 down first, then hit the math button, then scroll over to the probability menu, scroll down to the third option, which is n choose r, select it, and then input the smaller number. So it's 4 choose 0, and so that spits out the number 1. So we're doing this calculation here. 4 choose 0 is 1. Then we have 1/2 to the 0 power, which anything to the 0 power is 1. Then we have 1/2 to the 4th power. So that's 0.5 raised to the 4th power. And that gives us 0.0625. So we see what the probability is, 0.0625, which, by the way, is equal to 1/16. Okay, so that is the first probability, 1/16. Now we can use the formula to calculate all the other probabilities. So the probability that x equals 1 will be 4 choose 1, 1/2 to the 1 power, 1/2 to the 3rd power. So I bring back up the 4 choose 0, but now I can change the 0 to a 1, get my result. 4 choose 1 is 4. 1/2 to the 1st power is 1/2. And 1/2 to the 3rd power is 1/8. So that's 4 times 1/2 times 1/8, which is 4/16, which is 1/4. 1/4. So if you continue to do this process using the formula, you'll get the you'll get the following results on. Let's do the last one that we need to do, because we'll see that this is actually symmetric distribution. So the probability of getting a 2, that's 4 choose 2, 1/2 to the 2nd power, and 1/2 to the 2nd power. So to get 4 choose 2, we bring up 4 choose 1 again, change the 1 to a 2, hit enter, get a 6. Then we've got 1/2 squared, which is 1/4, 1/2 squared, which is 1/4. So this is 6/16, which is equal to 3/8. And ignore that. Okay. So 3/8 is the probability of getting a 2. And then what we would see if we kept on going is we would have a symmetric distribution here with a 1/4 for the 3 and then a 1/16 for the 4. So we go up to 3/8 and then we come back down. So that's how we compute the probability distribution for this particular random variable. These last two numbers you can get by going through this calculation again, and you'll see that you get the same results. Okay. So one last example for this section, and I can really do a ton of examples. They all sort of boil down to the same thing. So in this case, I'm going to take away all the words. We're not going to worry about what the context is. I'm just going to tell you what the probability of success is, how many trials there are, and what is the probability that you want to compute. Okay. So we know the probability of success is 0.25, and we have 40 trials, and we're interested in what is the probability that x is greater than or equal to 16. Okay. So since binomial experiments are the trials of a binomial experiment are all independent, we find out that the probability of x being greater than or equal to 16 is equal to the probability of x being equal to 16 plus the probability of x being equal to 17 plus the probability of x being equal to 18, all the way up to the probability of x being equal to 40. So since the trials are independent, finding this particular example probability amounts to summing up all of these individual probabilities. So this is tough, as we'll see. Just computing the first probability, p equals 16, which is the same as, just in case you're wondering, is the same as this. So we shorten this to this. Well, with all these particular numbers, we see that this probability would be 40 choose 16, 0.25 to the 16th power times 0.75, which would be our Q, to the 40 minus 16 power. Okay. So quickly, we're going to find out that this is a rather beastly computation. So to find the binomial coefficient, 40 choose 16, we use the function again. But now we change the numbers to 40 and 16. And we get a very hideous number that we can't even write down in its entirety. It's huge. Yeah, there's no way to actually write it out explicitly. So we see that this is equal to the 40 choose 16 is, I'm going to round, 6.29 times 10 to the 10th power. So a very large number. Then we've got 0.25 to the 16th power. Which is a very small number, 2.33 times 10 to the negative 10. And then we have 0.75 to the 40 minus 16th power, which is 24. And that again is going to be a very small number. So all of this is 0.0010. We'll just leave it there. Okay. So those are all the numbers involved. And we can see that when we put it all together, we get an answer that is 0.0146557. Now this result is actually a little wrong because we did a lot of rounding because we had all these big and very big and very small numbers. So it's approximate, but this basically says that the probability of having 16 successes out of 40 trials, where the probability of success is 0.25 and the probability of failure is 0.75, is roughly 1.4% or 1.5%. Okay, so you can see that if you had to do this for all of these numbers, P16, P17, all the way up to P40, it would take you a long, long time. So let me show you how to do it with the calculator. Calculator has tools. Okay, so the main tools we're going to use, we're going to get by hitting the second button and hitting the vars button. And this is going to bring up a bunch of probability distribution functions. And if I scroll down, eventually I get to two functions. One is Binompdf and one is Binomial Cdf. Okay, both of these are used in different contexts. Okay, so let's look at Binompdf first. Okay, Binompdf is precisely the binomial probability formula. So this function will spit out the answers for the binomial probability formula without you having to do all the individual parts. Okay, so for instance, for the calculation we just did, P of 16, where we have 40 trials and the probability of success is 0.25, in order to get that answer out of the calculator, we would tell it first how many trials there are, 40, comma, what's the probability of success, 0.25, comma, how many successes are we interested in computing, which is 16. So if I put all that information into this function, it'll spit out an answer, and you can see that that's very close to what we computed. 6835229. Okay, so this is the exact answer, or as exact as it needs to be. And this was our approximate answer. So we were pretty close, but it was a lot easier to just punch in the parameters into the calculator and get an answer. Okay, so Binompdf is the same as, so let me just say this, P of xk in general for a binomial problem can be computed by choosing the Binompdf function and then telling it what n is, comma, what p is, comma, what k is. Okay. Now there is another function that we can use that for this particular example will be super useful, because in this case, we're still computing all these individual probabilities. And while this definitely makes it easier to get each of those individual probabilities, it's still a lot of work. I mean, we still have to do this 24 times. That's a lot of times. It'd be great if there was a shortcut, and there is. So we have another function, which is the Binomial Cdf. And this tells you what the probability of, it tells you what the probability of getting less than or equal to k successes is. Okay, so this is the Binom Cdf. And here you have the same inputs, n, p, and k, but the meaning is different. So here we're computing the probability of getting 0 successes, plus 1 success, plus 2 success, plus 3 successes, all the way up to k many successes. So this counts up from 0. Okay, so if I wanted to use it cleverly to solve the problem that we have on hand, what I would do is pull it up, Binom Cdf, and then I tell it it's 40 trials. The probability of success is 0.25. And then what I would do is say, tell me what the probability of having at most 15 successes is, which is 1 less than 16. So if I do that, then it tells me that the probability that x is less than or equal to 15 is 0.9738. I was rounded there. Okay. Now, at first glance, that doesn't seem very useful, except we remember that we have the complement rule. So if I want to find this probability, then I can use the complement rule and say that that probability is equal to this probability. So all I have to do is take the answer I got here and subtract it away from 1. So 1 minus the answer that we just got is equal to 0.026244884. So that was a lot quicker than trying to do this by hand, one by one. Okay, a lot quicker. Now there is a way to do it without using the complement rule, kind of, sort of. We still have to do something similar. So really, this is truly the best way. So I'm not even going to try to confuse you by showing you other ways. This is the best way to do one of these sort of problems. So this is an at least probability, at least 16 successes. To do an at least probability, remember, the best way to do an at least probability is to use the complement rule. And this is the way that you use the complement rule in this context. Okay, so that concludes section 7.3. This is a pretty significant section. I know that it might be a bit daunting to you at first, but you'll see, especially using these calculator functions, that this section can ultimately be pretty easy to work with. So I'll assign some homework and have you guys work through it, and very likely put up another problem session for this section. Okay.